All right, you know what I look like. Anyway, and I know what you look like. So we're even. All right, so anyway, I was asked to. And I like doing this too. I found that this helps. But all right, for some reason, problem number one was one of the ones I was asked. But it says find the power dissipated in this cord. So I haven't turned on my ladybug yet. I don't need to do that. It always takes a second. So we're going to do it for 1, 5, 7, and 12, and I'll probably break it up into a couple videos, and then I'll also add screenshots of these notes. Or actually, what I'll do is I won't make them screenshots on the top hat thing. I'll just do it. I'll just send them to you via Canvas is on an email. All right. So anyway, so problem number one. All right. So what's power? What's power? If it's 5 amps, power is I times V. Might have been going, well, I don't know what the voltage is. I don't care. What does V equal? V equals IR. They give you the amperage, they give you this. So, well, you could go ahead and multiply those two together if you wanted to, and then get V in, or you could just skip that step and do that. We're moving on. All right, problem 5. And then they just made the image a little bit smaller. Okay, so problem 5. What's this one say? Oh, use the table below. Suppose that you want to double a copper's resistance. To what temperature in degrees must you raise it if it's originally at 18 degrees centigrade? Oh my gosh, I haven't talked about these in class. No wonder you guys are asking so many questions about this. Oh, whoa. I kind of did this in a passing shot, didn't I? So copper is 3.9. So this is the alpha thing. Suppose you want to double a copper wire's resistance. To what temperature in degrees must you raise it if it is originally at 18 degrees centigrade? Okay, I want to double its resistance. Its coefficient, so I want to double its resistance. All right, I probably should have looked this up before I started. Anyway, here's the deal. I'm going to stop here. I'm going to look this sucker. Well, it's something like this. It looks like this. R, resistance R, because it changes with temperature. R nu is equal to R naught times 1 plus alpha, which is our coefficient of resistivity, times delta times the change in temperature. Okay? So we want to make R naught, we want to make this equal to then this is simple. All right? And it's the same thing we're doing with chapter. So in other words, we want the new one to equal 2 times R naught. All right, well, if we go ahead and just plug this in, we go, okay, I got this, 2R naught is equal to, sometimes you just got to dive in like I just did. Is equal to 1 plus alpha times the change in T. So I've got T final minus 18 in this example, all right? And they gave me that alpha on the chart. And I think what was probably messing you up was they didn't give me R naught. Well, I don't need R naught. I didn't have those two cancel. So I've got 2 is equal to 1 plus alpha times T final minus 18. You might be going, well, what does that do for? Well, look, subtract 1 from 1 is equal to alpha times T final minus 18. And alpha is on that chart. You got that. Same thing happens with problem 7 here. Let's take a look at problem 7 real quick. And then I'll go to a new thing so we're doing 1, 5, 7, and 12. So here's problem 7. 7, the filament, This one looks hard. What was the one where people had to double it? Was that 9? No. Oh, it's 12. Was it 12? Sorry, I'm kind of... No? 10? Wasn't there one where we had... No, that's easy. 13? I'm sorry, I'm wasting your time. So let's go back to problem 7. All right, and we'll start problem 7 with the next one. Write an equation for the initial current that allows, that flows through the filament when it is initially turned on, when it is still at room temperature. Okay. All right, so we can do that. We can do that. So we'll write, but I'll do that in the next video. I'm sorry, I kind of wasted your time there a little bit.